All right, let's do a couple example problems of doing integrals in spherical coordinates. So the first one says evaluate this integral and sketch the solid whose volume is given by the integral. So if it's a volume, that should come from integrating over a solid region D, the one function, dv. Because you're going to add up, that's going to add up all of the little pieces of volume. You add up all the total pieces of volume, you get the total volume. But in this case, we've got 1 times rho squared sine of phi d rho d theta d phi. Okay? So dv is equal to rho squared sine of phi d rho d theta d phi. That's the volume element in spherical coordinates. And now the rhos, it says, are 0 to 4. So the rhos are going to go from 0 to 4. The thetas are going from 0 to pi over 2. And the phis are going from 0 to pi over 6. So, well, I guess we could just do the calculus, compute the integral, and then we'll talk about how the bounds here that they've given us actually relate to one of these solid pictures down here. Okay, so first just do the calculus. So we've got 0 to pi over 6, 0 to pi over 2. Integrate rho squared, we're going to get rho cubed over 3. Sine of phi evaluated from 0 to 4, d theta d phi. Okay. And when we evaluate 4 cubed, we're going to get 64 and then divided by 3. So I'm just going to pull that outside of the integral, 64 over 3. Of course, minus 0, so that's just 0. And then 0 to pi over 6. 0 to pi over 2, sine of phi, d theta d phi. Okay, so now we're going to integrate with respect to theta. So 64 over 3, 0 to pi over 6. So sine of phi, that's just constant with respect to theta, and then we integrate d theta, we'll get theta, evaluated from 0 to pi over 2, and then we have d phi. That's going to give us pi over 2 minus 0, so that's just pi over 2. So now we'll have 32 pi over 3, because pi over 2 times 64 over 3 is 32 pi over 3. And then we have to integrate from 0 to pi over 6, just sine of phi, d phi. Of course, the antiderivative of sine of phi would be negative cosine of phi, evaluated from 0 to pi over 6. And then we're going to get 32 pi over 3, negative cosine of pi over 6 minus negative cosine of 0. And that would be 32 pi over 3 times, let's see, that's cosine of pi over 6. Pi over 6 would be a 30-degree angle, so cosine would be the long side, so that should be root 3 over 2. So negative root 3 over 2, and then plus 1. All right, so the correct answer should be 32 pi over 3 times negative root 3 over 2 plus 1. And they're saying that it's 16 over 3 pi 2 minus root 3. So is that the same as 16 over 3, 2 minus root 3 pi? And I think so, because they've just, the pi matches, the 3 matches, they've just taken 2 times 16 is 32. I just have 1 times 32. And then if you multiply that 2 in there, you'd get root 3 instead of root 3 over 2. So that's the same answer. Okay, so the calculus is more or less just doing the antiderivatives 3 times and working out the answer. The interesting part of this problem is why do these bounds here, what region does that relate to? Okay, and so let's take a look at that a second here. So we had 0 to pi over 6, we had 0 to pi over 2, we had 0 to 4, and that was d phi d theta. No, sorry, how did they have that? D rho d theta d phi. D rho d theta d phi. So the rhos are going to go from 0 to 4. So that really means that we're in between the sphere of radius 0 and the sphere of radius 4. So it should be sort of everything inside the sphere of radius 4. But then the thetas are only from 0 to pi over 2. So if the thetas are only from 0 to pi over 2, well, here's theta equals 0, and here's theta equals pi over 2. So we're really only in this chunk of it. So you can kind of think of chopping off that sphere according to those two half planes down there. So you're not going to get a full sphere, you're just going to get a chunk of a sphere. And then the last thing it says is the phis go from 0 to pi over 6. Well, phi is measured down from the z-axis. So here would be phi equals 0, and here would be phi equals pi over 6. So we're really getting just the bit of sphere that's sort of between here and here, and then up to the top. So I'm thinking we should get probably it's a little hard to tell, but I'm thinking it's probably this picture right here. Or maybe it's this picture right here. If this is an angle of pi over 6, here's rho equals 4 down to 0, and then we want everything between theta equals 0 and theta equals pi over 2. I think this picture looks good, but the angle comes down too far. That would be like pi over 3 instead of pi over 6. So kind of made a mess of it here, but this appears to be the correct drawing there. All right, so that's kind of an interesting problem. You might think about what are some of these other shapes here. This would be theta equals 0 to pi over 2, phi equals 0 down to pi over 2, and then rho equals 0 to 4. This one looks like a particular phi down to phi equals pi over 2, so maybe this is phi equals pi over 6 down to pi over 2. So you're getting sort of different phis for different ones of those drawings there. All right, a second example problem, and in this example problem it says spherical coordinates just do this triple integral, but they don't tell you the bounds. And they say the region E lies above this cone and below this sphere. All right, so let's see if we can kind of draw a little picture there. Phi equals pi over 3, that's a cone, right? There's the pi over 3 cone. Here's 0, pi over 3, right? And they want us to be above that cone, but then below the sphere. So there's like a sphere of radius 1, and we're kind of inside of that region there. So what you want to think of is in sort of the z land here, that would be this pi over 3 cone, and then we want to be above that, but then there should be a sphere up here of radius 1, and we want to be below that. So when we write down our triple integral here, I think we want the rhos to go from 0 to 1, because given a point, you're going to go out until you hit the sphere. We want the phis to go from, well, 0 to pi over 3, right? There's phi equals 0, there's phi equals pi over 3. We want everything in between there. And then what about the thetas? Well, for thetas, it looks like there's no constraint on the thetas. So the thetas are just going to be the whole circle, which means thetas are going to be 0 to 2 pi. All right, and then the function they gave us was y squared z squared. So then we can use our formulas for what y and z are in spherical coordinates. Okay, so if you have those written down, y is equal to rho sine phi cosine of theta, or sorry, rho sine phi sine theta, and z is rho cosine of phi. And we can talk a little bit about why that's the case. So remember, in spherical coordinates, we have this triangle here. This is r, this is z, and that's phi, and there's rho. And so when you do the cosine of phi, you get z over rho, and therefore z is rho cosine of phi. That's based on that sort of right triangle right there. So that's the formula for z. And the corresponding one for sine of phi would give you r over rho. And so rho sine of phi gives you r. And y is, of course, r cos theta. Or sorry, r for the y coordinates, r sine of theta, rather. And so if you know what r is, then you're going to get rho sine phi sine theta, which is what we've got right there. So you can think of that triangle really gives you what these are. And since the integrand was y squared z squared, we'll end up with, well, what are we all going to have here? We'll have y squared, so that'll be a rho squared. Rho squared. Then we'll have sine squared of phi. Then we'll have sine squared of theta. And then z squared will give us a rho squared cosine squared of phi. All right. And then we need dv, which is rho squared sine of phi d rho d phi d theta. All right, so with that in hand, we can actually sort of do the integral now. 0 to 2 pi, 0 to pi over 3. And how many rows do we have here? Oh, 2, 4, 6, I guess. So that's going to be rho to the 7 over 7 from 0 to 1. And then everything else, which maybe we'll accumulate this stuff up. We've got a sine cubed of phi. We've got a cosine squared of phi. And we've got a sine squared of theta. D phi d theta. All right. Well, that's going to give us 1/7 when we evaluate it. So I'll just move that outside the integral for simplicity. And then we're going to have to integrate, what's next? D phi. So we're going to integrate the phis. Well, this looks like a trig problem here with sine cubed of phi and cosine squared of phi. So I think what we're going to do is write this as sine of phi, and then there's two more, which would be sine squared. Well, sine squared is 1 minus cosine squared, like that. And then we have cosine squared of phi, sine squared of theta, d phi, d theta. And the reason we're doing that is in order to evaluate that integral, we need to do a u substitution. And if we do u equals cosine of phi, then du will be negative sine of phi d phi. And there's a sine of phi d phi right there, and everything else is cosines. So let's work that out. 1/7 integral from 0 to 2 pi. Integral, this will be in terms of u now. Well, we don't have a negative, do we? So let's add the negative. And then we'll add the negative there. So now I've got, this is my du. So there's du, I'll put there, du d theta. And then what else is u? Well, we've got 1 minus u squared. And then there's a u squared. And then, what is this? This is just a regular sine squared of theta. Okay. And the bounds, well, u is equal to cosine of phi, so if phi is equal to 0, u would be cosine of 0, which is 1, so there's a 1. And if phi is equal to pi over 3, u would equal the cosine of pi over 3, which would be 1/2. So there's 1/2. Oh, and I forgot the negative. Okay, that's a u substitution. So I'm going to now evaluate that integral. And to me, the integral looks like, what is that? U squared minus u to the 4th. So that's going to be u cubed over 3 minus u to the 5 over 5, evaluated from 1 to 1/2, and then sine squared theta d theta at the end. And what's that going to work out to be? Well, 1/2 cubed is an eighth. So 1/8 over 3 is 1 over 24. And 1/2 to the 5th is 1 over 32. And 1 over 32 divided by 5 is 1 over 160. That's what we get when we plug in a half. Minus, plug in 1, 1/3 minus 1/5. Sine squared theta d theta. Okay. And I'm just going to add those up here. 1 over 24 minus 1 over 160 minus 1 over 3 plus 1 over 5. If we put it all together, I get negative 47 over 480. So negative 1/7 times negative 47 over 480 times the integral from 0 to pi over 2 of sine squared theta d theta. Okay. And if I multiply that by negative 1/7, we end up with 47 divided by 3360. Okay. Now we have to integrate sine squared. Well, sine squared doesn't integrate very well, so we write sine squared as 1 minus cosine of 2 theta over 2. And that's called the half angle formula for sine squared. And now we can integrate that correctly. And that's going to give us what? 1/2 of a theta minus a sine of 2 theta over 4, because the antiderivative of cosine is sine, but we got 2 theta, so we get a 2, and then we have to divide by 2, and that's got to be evaluated from 0 to 2 pi. Okay, so 47 over 3360, that's going to give us pi minus 0 minus 0 minus 0, I think. So that's great. So it's just pi. So 47 pi over 3360. And we'll see if we got the right answer there. 47 pi over 3360. Boom, right there. Okay? So the interesting part of this problem is, can you read the paragraph and convert it into, a region that can then be integrated? That's sort of part one. And then can you do the calculus and get to the right answer in this case? All right, so there's a couple examples of spherical coordinate integrals. I hope you find that helpful, and we'll see you next time.